Our presenter today is Bill Donovan. Bill is the engineering manager for Thor Labs' Advanced Photonics Division. In this role, Bill oversees our team of engineers in manufacturing processes related to fiber and free space optical components and subassemblies. From a background in physics, Bill started at Thor Labs over 12 years ago as an optical design engineer where he designed custom optics and optical systems to meet our customers' application needs and many of the optics you will find in our catalog today. Without further ado, Bill Donovan.
Thank you, Matt, and I appreciate the kind introduction, and thank you for the assistance with moderating today. And thank you to all of you for taking time out of your day, hopefully to learn a thing or two about optics. At the very least, freshen up on some core concepts you may not have thought about in some time. Today, I will be talking about some of the fundamental principles that govern light, with an emphasis on how it behaves in response to matter, in an effort to bring understanding to these concepts, as well as to show why they are meaningful to us. We will then transition to some common components. Taking it a step further, we will discuss how some of these items are produced. In understanding how these elements are manufactured, we begin to see why various techniques may exist. Much of what will be covered here will serve as a foundation for a series of webinars to come. So keep a lookout for more. Much of the content covered here can also be found throughout the Thor Labs website in a variety of formats. Others borrowed to help create a complete picture. There are many extraordinary things that we can observe and do with light. This science and technology of light is known as photonics. In much of the same way as electronics utilizes the electron, is described by principles such as Ohm's law, and employs circuits, photonics utilizes the photon, is described by principles such as Snell's law, and employs the optical train. Much of it starts with the basic ideas that will be covered here. The rigors of deriving these theories can be instructive, but for the sake of time, let's just accept that they are true. The concepts themselves are fairly simple, and this is sufficient for making use of them in general practice. These concepts lie at the core of understanding and utilizing light in a wide variety of ways. They allow the photonics industry to exist, even in the most complex and cutting edge of applications. In particular today, we will cover basic intro to light. We'll touch on geometric theory, covering areas of refraction, dispersion, reflection, touching on the theory of each of these, as well as a number of examples and some of the ideas and concepts within fabrication of these items as well. Beyond that, we'll step into wave theory, where we'll enable ourselves with an understanding of vectors and polarization, and moving from there into Fresnel reflection, polarizer types, and some interference so that we can discuss a little bit of thin film coatings as well. All of this is everyday life at Thor Labs, as seen in an example here of our collimator product line. We utilize the concepts in design and analysis, bring them to life in production, then take them to market, knowing how they are commonly used. So here's a fun little fact of the collimation area that we have. You see in this image a demonstration or illustration of the production area. And what's really cool about this is that almost everything that makes up this assembly section is a Thor Labs catalog product, from the table to the optomech, the optics, the beam analysis equipment, the motion control, and even some of the software. But first, what are we dealing with? Well, light is a self-propagating electromagnetic wave. The electric and magnetic fields are perpendicular or transverse to the direction of propagation, as we see here. Light behaves as both wave and a particle. This electromagnetic radiation is quantized as a photon. A photon's energy is proportional to the frequency of light. This proportionality is defined by Planck's constant. The electromagnetic wave propagates at the speed of light in vacuum. It is represented by the letter c and travels at approximately 300 million meters per second. The distance between the peaks of intensity define its wavelength, denoted by the Greek letter lambda. As we know, over the visible, this corresponds to its color. Beyond this, it dictates what spectrum it falls into. For example, ultraviolet or infrared. We could see that by this illustration down here. Some of the different ranges throughout the electromagnetic spectrum. In optics, we tend to represent the wavelength in values of nanometers or microns. There are a few different ways that we consider light, depending on what we are trying to understand. Primarily, we understand it through geometrical, wave, and quantum theory. Today, we will concern ourselves mostly with geometric and wave theory. This will enable us to explore different aspects of refraction, reflection, some ray tracing, interference, polarization, and Fresnel reflection. Slow down. All right, well, that's what light does when it interacts with a different medium other than the vacuum. Some of the more significant behaviors of light occurs at the boundaries between materials. This is in large part due to that change in speed of light. This change in speed is represented by the index of refraction, typically referred to simply as index. Index is typically denoted by the lowercase n and is defined here. The index of refraction varies with wavelength, so it is best to know which wavelength we are describing when specifying an index. We often utilize common spectral absorption peaks, or Fraunhofer lines, to establish a standard of reference for these wavelengths. In order to broadly represent the range of the visible spectrum, we select F, D3, and C as commonly used lines. They correspond to 486 nanometers, blue, 588 nanometers, orange, and 656 nanometers, red. D3 most commonly referenced of them all, and typically denoted by a lowercase d. The index of refraction for the D line is then represented by n subscript d. And here are some of the common transmissive materials and their indices. In most cases, assigning air equal to 1 is precise enough. Some IR materials do not transmit at 588, and so they are defined at wavelengths that they are generally used at. We see these two, silicon defined at 10 microns and germanium defined at lambda equals 13 microns. So with that, we've touched on the basics and should allow us to get into a little bit more of the geometric theory and particularly refraction. So with an index understood, we dive into refraction. Here we see light represented in a simple ray trace, portraying the behavior at a boundary given two transmissive isotropic materials with a smooth boundary as is provided by a common polished optical surface. Due to the change in speed when reaching an interface at an angle, light will bend at this surface. If the light is transitioning from lower index material to higher index material, as we see here, it will bend towards the normal axis. If going from high to low, it'll bend away. To aid in understanding why this happens, a typical example of a marching band moving from pavement to mud is given. And we could see that in this illustration here. If you were to imagine the band members who leave the concrete and move to the mud are slowed by trudging through the mud. This slower pace on one side causing the formation to shift direction. In truth, when I first learned this, the example was instead of fat men in Speedos holding hands running into the ocean. This has definitely served as a powerful mnemonic device for me. We also see from this illustration in particular another method of representing how waves of light propagate. So not only the ray trace that we see here, but also in the wavefront form of lines as it moves forward in propagation. The relationship between angles is described by a simple yet essential formula known as Snell's law. We can define that as n1 sine theta 1 equals n2 sine theta 2. Alternatively, we can represent it with I for incident and R for refraction, which enables another powerful memory device that I've learned as ni sni ner snur. And so it's this bending of light that gives lenses the power to do what they do. In fact, the degree in which a surface converges or diverges light is referred to as optical power. This power can be rotationally symmetric, as is found in spherical lenses, or in one axis, which is true of cylindrical lenses. Many factors determine which shape and size is best for a given scenario. This contributes to around 3,000 different lenses available in the Thorlabs catalog. We see some of them, or at least an overview of them, in this slide here. A couple of the cases being our plano-convex, biconvex. We have our various concaves, various meniscus forms, best forms. Mentioned some of the cylindricals that allow for us to focus in one of the axes. We have some other novel types, as well as a variety of different options for aspheric lenses as well. If you're looking for further information on which lens to choose from, please look for the lens tutorial on our website. Another driver of available lens types is how they are produced. Lenses turn up throughout ancient history, but the practice of grinding and polishing really emerges in late 13th century. Progress through the centuries brings us to the techniques for producing lenses and plano optics known today as conventional fabrication. The methods employed lend themselves to large tools of uniform spherical surfaces, leading to the ability to batch several pieces to a block and produce low surface error parts. This equipment can be relatively inexpensive as well, but in the hands of a highly skilled operator, still produce better plano and spherical surfaces than most advanced equipment today. And just a quick look at some of the images we have here. On this top portion, we're illustrating a variety of plano parts loaded onto a common block. By loading it onto here, as mentioned, it allows us to batch a large quantity of pieces. It also allows for a common or more common workpiece size for loading into our equipment, as you see here. This also allows us to maintain more consistency to a lot of the dimensions across the variety of parts too. In addition, it might not look like much, but here's an image of a couple of spherical pitch tools for producing some high quality spherical surfaces as well. This pitch allows us to have more of a conformal fit to the surface, which will produce a more even finish, minimizing any of the mid-spatial frequencies that might occur as a result of common techniques. And that said, there are a few reasons computer numerically controlled equipment would be employed as well. One advantage found in their ability to produce aspheric as well as freeform surfaces. Despite some trade-offs, a single element asphere can do more than numerous spherical elements combined. allowing them to work in more confined spaces and/or effectively collect highly diverging light sources. Both production methods find use on the Thorlabs production floor and are seen in the products we provide. And a quick peek at some of the CNC images here as well. We see first inside one of the CNC machines where we see one of the lenses or items that were our workpiece here is fixtured up into the machine, where we then have our additional axes of rotation that are brought in so that we can contact at a surface, which allows for, as we discuss, some of the unique capabilities of the CNC. And then just some additional nozzles for supplying the coolant to the surface as it grinds or polishes. And then additionally, showing an added feature that we have of the ability to then take our optics into a magnetorheological finishing setup. Here we see the workpiece fixtured and being passed through this ferrous fluid that we know the defined signature of removal for the part with. And here we can use subaperture removal techniques to improve even further the finishes beyond a standard polished part. Since index changes with wavelength, it becomes apparent that Snell's law would lead to different angles of refraction for different wavelengths. This leads to separation of white light into its components. This separation is known as dispersion. Alternatively, due to reciprocal nature of most optics, this principle can also be used to recombine wavelengths into white light. In some cases, dispersion isn't desirable, but in others it is. An equilateral prism, which we see an example of here and have probably seen before, takes advantage of high dispersive materials and geometries lending themselves to more oblique incidences to separate the wavelengths of light. Sometimes this dispersion is not desirable. When trying to focus light in a lens system, for example, it becomes something to contend with. For this reason, multi-element lenses are employed. For instance, pairing a crown and a flint glass with complementing characteristics of high to low index and high to low dispersion, an achromatic doublet is produced. These elements have the added advantage of significantly reducing spherical aberration and coma too. By comparison to the aspheric lens, these optics are also much less sensitive to alignment. We see in this illustration here that we bring the variety of wavelengths from 400 to 800 nanometers of light to a common focal point, achieving a much smaller spot and less chromatic blurring than we would observe from a plano convex lens. Additionally, we see that with a beam that's coming off axis, we have less of this area of confusion and can bring the spot to a closer focus once again in comparison to the plano convex lens. And so quickly we begin to find special cases of Snell's law. As I mentioned, going from a higher index to a lower index causes us to bend away from the normal axis, as we see here. This leads to a point known as the critical angle, where light no longer refracts, but is totally reflected. Emphasis on the word totally. Any angle greater than the critical angle will experience total internal reflection. Even the best possible mirrors couldn't offer 100% reflection, definitely not over a wide range of wavelengths. This leads to many varieties and applications of prisms, many of which also produced by Thorlabs and found in our catalog. We see some of the examples here. A common use is with the right angle prism, for example, where we employ TIR off of a single surface to bend the light at 90 degrees. We also notice that these two surfaces that it enters and exits from are close to normal, so minimal translation or dispersion effects may occur there. Additionally, we can use the same prism in a different format to get a one-axis retroreflection of the part. Aside from that, we could also use 3 different surfaces in a corner cube configuration to achieve prisms that give us a 2-axis retroreflection of the image as well. We also see here an example of the roof prism, which gives us, once again, a bendit reflection here with a slightly different geometry in the image that would be produced. And then lastly, the Pelham-Broca prism, which we see here, which not only benefits from the use of total internal reflection, but its intent is once again for generating dispersion of the light that's incident on it. So this allows us to perform similar actions as what we had seen with the equilateral prism. TIR is also a driving factor in the usefulness of optical fibers. And this is described in greater detail by my colleague David Gardner in the Optical Fiber 101 found in the Recorded Webinars section. Reflection is simply described as angle of incidence being equal to angle of reflection. This is true whether it's TIR, the percentage of light reflected back at a bare surface, or that returned by high reflecting coatings or materials. It can be said that reflection is another special case of Snell's law, where N1 equals N2. So essentially that equation is boiled down to what we see here of theta I equals theta R. So just recapping on where we're at, we've touched on the basics, have run through a number of concepts involving geometrical theory. So let's get into wave theory. So many forms of light we encounter have an arbitrary or random state. This means that there is a varying orientation to the light's electric field vector, as seen in this mess of colors of different waves observed in the middle section here entering these polarizers. If looking directly into the oncoming light, the electric field vector's oscillation would demonstrate more of a random walk than the smooth oscillation we tend to associate with the wave. But for better understanding how this light behaves, it's best to break them down into their vertical and horizontal components. So we're shown here in the EX and the EY. By doing so, we can better understand how the light behaves at a surface and in other cases. By doing so, we can better understand as well light existing purely in these states and how they would be referred to as vertically polarized or horizontally polarized states of light. And they are illustrated here on the back end of the polarizers and in their vector notation here and here. So with that, we can dive into reflection. And starting with the complex expression of linearly polarized plane harmonic wave through a homogeneous medium, with some mathematical derivation and application of Snell's law, the percent reflectance of a surface can be worked out for parallel incidence and perpendicular incidence. We see here, so they may also be referred to as P and S polarization, S from the German word for perpendicular. This was deduced by Augustin Jean Fresnel, who first understood light to be a transverse wave, and thus this principle bears his name, Fresnel reflection. Similarly, transmission can be worked out. For quick analysis, a simple assumption is often applied. Absorption, in this case, is defined as A, and for many optical interfaces is negligible, leading to 1 minus r, providing us with the value for transmission. You must take care, though, to understand when this assumption is safe to use. So now we can plot the change in reflectance as we vary our angle of incidence from 0 to 90 degrees for a standard material that we see here in the example of MBK7. At normal incidence, we observe a reflectance just over 4% per surface. As we move along out into the wider angles, we see that the point between S and P begin to separate. This gets more significant. This is pretty significant even at 45 degrees, as we see here, which is common for its convenience of a 90 degrees reflection, obviously. And a good contrast to MBK7 we see here with germanium. The high index of refraction leads to a much greater reflectance value at normal. So remember, this is roughly around an index of 4, and we see a percent reflectance of nearly 40% as a result. These higher index materials also see a much greater separation of S and P. And keep in mind, so this is just for one surface here. And this is why a lot of times that when using any of these infrared materials, it's often essential for us to use coatings, anti-reflective coatings, that is. So you may have noted with both materials where RP went to 0. This is known as Brewster's angle. The polarizing effects of a reflection can further be tailored to our needs through the use of optical coatings as well. But reflection is only one way that a degree of polarization is established. Various types of polarizers benefit from dichroism. These have benefits but can have limitations as well of power handling due to the absorptions, as well as sensitivity and certain factors such as stress or angle of incidence. They include film-based polarizers, originally developed by Polaroid, nanoparticle, and wire grids. In addition to that, we also see that materials themselves can exhibit different index of refraction along different axes of propagation. This inhomogeneous behavior is often observed in crystals. It is known as birefringence. This bias can lead to some interesting ways of manipulating polarized light. These crystal polarizers are a bit of a specialty of ours. Fabricating prisms from calcite lead to many geometries with various benefits. Let's take a look at some of them here. We see with this example the Glan laser or Glan Taylor type. In this configuration, we observe that we can completely pass the extraordinary ray with very little translation occurring, while also rejecting our ordinary ray. This is performed by the fact that the two indices fall in between their total internal reflection of the angle that's chosen for this part, allowing the ordinary to TIR while the extraordinary does not experience that phenomenon. Further enhancing the extinction ratio of these parts, we also provide a double Glan Taylor or double Glan laser configuration as well, utilizing 3 prisms to produce these 2 locations of TIR. Beyond that, we have the availability of the Glan Thompson, which allows us to achieve similar effects while not having to create that fine air gap to allow for TIR to occur, but the orientations of the crystals in these prisms themselves to do so. Beyond those, we see our examples of the Wollaston and Roshan type polarizers. These provide outputs that follow pretty normal or close to the incident light with small separations or smaller separations than the near 90-degree kick out of the Glan-Taylors and Glan-Thompsons. Beyond those, we also see our beam displacers or walk-off type polarizers as well. Beyond that, with a crystal or optic axis normal to propagation, we see a special case of polarizer known as a wave plate or a retarder. Passing through these parts that are essentially plano-plano with parallel surfaces, we can see some interesting phenomenon that occurs here. So passing through the material of one component, the electric field we see lag with respect to the other component of the electric field. Two common forms exist here, the quarter wave and the half wave plates. We see here the delay of our quarter wave plate with the 90-degree phase shift, allowing these two components to sum to a circular polarization state being created as a result. In addition to that, we also see our half wave plate, where a linear input is then shifted to create a rotation over about the optic or crystal axis here to rotate our output polarization while maintaining linear states. By pairing plates, we can produce designs that are less sensitive to wavelength, called achromatic, or even in some cases, super achromatic wave plates. And of course, just like with other optics, the grinding and polishing of these parts are very critical, but some other components come into play here as well. For example, it is important for us to orient the parts or the initial material in a configuration where we know that crystal axis well and can tolerance it tightly, so that the optics that are ultimately produced from these enable the characteristics and properties that we desire. Beyond that, we also look then to shape to those dimensions to allow for those performances to occur. And with doing so, some of those dimensions are highly critical and require some angles to precisions on the order of a few arc seconds in some cases. So yeah, pretty difficult to maintain at times, but we do it. And then lastly, once we have those shaped up and have ground and polished the parts to their form, it's important that we block them in a way that we can maintain those angles for further fabrication and production of those optical surfaces to the quality that we require. In addition, that blocking technique is important to us because we actually employ methods that allow us to use no epoxy at those interfaces between the block and the optic. This allows us to maintain high levels of flatness, really critical levels of parallelism, and hold very tight levels of thickness as well, which is super critical on wave plates where we're talking about stuff on the order of optical waves in terms of accuracy that we need to maintain for the part to behave similarly across the entire aperture of this part. And we do this. So this is all balanced out with at the same time trying to achieve a high optical finish to that surface. In addition to this, it's also important that we select the right materials for the job. So in the cases of many of the polarizers, we see that calcite is often employed. A reason for the calcite to typically be utilized in these cases is because of the larger difference in the index based on the ordinary and extraordinary ray, or at least what they would observe. With this calcite and that large delta N, for example, if we take it back to the example of the Glan-Taylors that experience that total internal reflection to split those rays, that larger delta n gives us a lot more wiggle room and ultimately more of an a larger angle of incidence to work with on that incoming light, as well as a wider range of wavelengths that can be accepted into those parts. On the flip side, in the case of wave plates, for example, we choose materials such as quartz, magnesium fluoride, or sapphire. And the reasons we do that are because, as I mentioned before, we want to maintain a low number of order of waves for the parts to actually be shifted through. This reduces a lot of the sensitivity and also enables some of that achromatic balancing that we do as well. The sensitivities I'm referring to being both thermal as well as some very minor angle components and wavelength as well. So just to remind ourselves where we're at this point. So we've covered the basics, we've touched on geometrical theory, we've hit on some of the components of wave theory and gotten through our polarizer types. And before we jump into interference, I would just like to touch on some of the highlights of what we've learned about material and what would help us in choosing the right material for the application or need that we have. So looking back, we've discussed the index of refraction. We saw that with lower index materials, we observe a lower Fresnel reflection. So for situations where we are not using a anti-reflective coating or something along those lines, that material might be more desirable. Another example is with the higher index materials where we see that the power of the lens is enhanced. We can focus at shorter distances, for example, and that might be a reason that we would desire a high index material. Additionally, we saw that with some of the prisms, we have desired dispersive properties of these higher index materials that we might want to employ. And then also, as we saw with the multi-element lenses, that a lot of times we want a combination of that lower and higher index material to correct some of the aberrations that may be generated with a single optic. Beyond that, we touched on a little bit of the polarization effects and what having a variation in our delta n can create, and some of the items that it leads to. Beyond that, we've alluded a little bit, but haven't discussed too much, is the transmission of the materials as well. And we see here in this plot a variety of different common materials, and over this log scale, we notice that there's quite a bit of a range to the various regions where we would expect the materials to operate well. And in most cases, yeah, we're looking for as high transmission as possible for the system, but there are situations where we actually want to attenuate the light, and there are a variety of different materials that allow us to do that. Some colored glasses allow us to more selectively choose spectral regions, similar to a bandpass or other features that may occur, as well as some that attenuate broad wavelengths of light more uniformly. Moving from the optical properties that we may choose, we also see that there's some obviously physical properties that might benefit us too. Some of those might just be the durability of the material. For example, sapphires are much harder than fluorides, so in many cases we may prefer to use that material instead. But not all the time does that give us the functionality that we need. Environmental and chemical resistances come into play a lot of times as well, and understanding these is often critical. And lastly, it's important to know what our thermal properties are, particularly in more sensitive situations or cases. So with that, we move into interference. And what enables us there is the principle of superposition. As is demonstrated here, when observing two waves meeting, three defined cases occur. So we see these two waves. When they come into contact as passing, we notice there's a case where there's constructive interference, and the amplitude of the waves is doubled when in phase. There's destructive interference, which we see here, where waves completely negate each other when out of phase, and partially destructive occurring in between these states. Interference presents itself through optics in a variety of forms. It even often serves us in many ways in the measurement of optics during production. Our interest in it here serves as the basis of optical thin film coatings. By applying a thin layer on a surface, we would observe two back reflections. For a quarter wave optically thick layer, these two reflections would experience a half wave offset. So we would see quarter wave in, quarter wave out. It's now delayed by a half wave. This would lead us to destructive interference, resulting in a reduced back reflection. From close consideration of the phase component of the electromagnetic wave, along with application of Fresnel reflection to thin films, we arrive at the quarter wave rule, which is shown here. The simplicity of the quarter wave rule is a powerful tool in designing optical coatings. It helps us understand the oscillation in %R as the optical thickness increases, allows us to achieve simple anti-reflective coatings as well. So we see here, in the case of a 1.72 index material, if we were to apply mag fluoride, which is typically a 1.38 index, we would see the percentage drop from 7% and diminish to almost 0 as we arrive at that quarter wave optical thickness. And as we continue to deposit the material, we would see it increase back to the initial reflectance of the bare substrate again, and continue to oscillate, so on and so forth from there. With a slightly more complex design, we would also be able to generate an anti-reflective coating that achieves nearly 0% reflectance as well for a single wavelength. This often has the characteristic shape of a V, where it gets its name, a VAR coating. Extending the quarter wave rule to multiple layers allows us to design more complicated coatings. Admittance plots are a common way of working out how a coating will behave at a single wavelength. Given that the quarter wave rule defines a circle in complex space, the equivalent index can easily be plotted. Applying well-established tricks can make coating more or less wavelength dependent as needed. So as we see here, a number of different layers are coated. So going from a 16th wave of low, 16th wave of high, half wave of, high, low, high, and then another quarter wave of low, gives us a lot more or a lot less sensitivity to the wavelength and really flattens out that V into a much more acceptable broadband performing coating here. Beyond that, we can see that we can extend it even further, and taking a look at just some of the common broadband anti-reflective coatings in our catalog, we observe that we can cover a range from 0.3 to around 15 microns with low reflections, in most cases around or less than 0.5%. That can be seen by a couple of the cases we see here with the A and what we refer to as the AB coating. Additionally, using similar techniques but with a half wave thickness, we can actually enhance the coating's reflectance. And we see that here with an example of our EO2 coating. And we do similarly with some of the other ranges of the dielectric mirrors too. In contrast to the dielectric coating, high reflectors, we also employ a number of metals. We see here the unprotected gold coatings, which give us a much broader range with a consistent level of reflectance. So not as high as the dielectric, but over a larger range, more enhanced. We also then offer items where these surfaces are protected, either for mechanical robustness or to prevent oxidizing, and then as well in some cases to even enhance the metal's intrinsic properties. For example, here, where we give a boost to the aluminum coating performance for better performance in the UV. Beyond that, we see various other approaches of design to these quarter wave and half wave stacks or near wave approximations there with much higher levels of thickness to achieve various other filters and beam splitters, which some of we see here, from the bandpass filter, the notch filter, some of our edge pass filters like the long pass and short pass, long pass shown here, as well as items that operate off of that zero AOI, in this case 45 degrees, with the dichroic beam splitters as well. A lot of this is enabled through the wide variety of different technologies that exist, and many of which that we employ here at Thorlabs. For example, we see a lot of cases where we utilize a variety of different physical vapor deposition techniques, like the thermal evap, electron beam sputtering, electron beam evaporation deposition. Some of these we enhance with an ion-assisted deposition approach as well. And beyond that, we also have some sputtering techniques too. Largely, we employ either ion beam sputtering or plasma-assisted magnetron sputtering. Beyond that, we have a couple of special cases where we use techniques like molecular beam epitaxy, spin coating, or plating. Taking a quick peek beyond those technologies at the physical equipment, we see that many of these systems are quite large. Part of this is to do with the batching of large volumes of parts, and also to enable some of the throws of the high energy material we're working with, in addition to just the operation having to occur within a vacuum for all of these processes. We see here some of the operators at the equipment. We see a look inside some of the equipment. This one being an example of one of our E-beam chambers, and this here being an example of one of our sputtering chambers. We could note the large size of the targets, and hence the power of some of this equipment, due to the fact that, just for a point of reference, these are around 8-inch wafers here, or 200 millimeters that we observe. And that's all I have for today. I hope this has been informative, and thank you for your time. Matt, I believe back to you.
Yeah, thank you, Bill. So it looks like we have a few questions that came in throughout. So the first one relates back to total internal reflection. The question is, why would you use TIR as opposed to a mirror?
Okay, yeah, great question. So as I mentioned, part of this has to do with the fact that, and as you saw later on in the discussion when we observed some of the mirrors, the metals reflecting, depending on the range, anywhere from the low to high 90%. And even in the cases of those dielectric mirrors, we see that they will operate pretty close to 100%, but still not, in most cases, 100%. I mean, in some really high quality mirrors, we do notice that we get very close, I mean, on the order of parts per million. But even those are typically, to achieve that, you achieve it at a single wavelength, and it's not achieved over a broad spectrum as well. And then additionally, it's not going to occur, or I guess I should say that it's also going to exhibit sensitivity to angle as well. So you're going to design those specific to a given angle.
Nice.
So I hope that helps.
Next couple of questions, sort of go back to polarizers. Can you discuss why there are so many gland type polarizers? What distinguishes them from each other?
Sure. So I think in large part it has to do a lot of times with whether the secondary beam is required or not. In other cases, yeah, I think just largely geometries tend to be a big factor in it. Some of them have varying extinction ratios that they perform. Others, yeah, it's a little bit more easy to collect the light if you're dumping that additional beam. Yeah, I think it's just a lot of cases of preference. Some areas where we're looking, where we have more of the beams that stay a little closer to inline, a lot of times those are brought back into interference or things of that nature to achieve some certain techniques.
All right. Another question about polarizers. Can you please recap again what are the advantages and disadvantages of cube polarizers versus plate polarizers?
Sure. So again, I think a little bit of it comes down to geometry. Generally, the cube polarizers will allow you to pass the light through without observing any displacement. Whereas when we see light through the plate, it'll displace slightly from the output. So our output's still parallel, but it's slightly off of the way that it came in, which can be problematic at times. But beyond that, then the cubes, for example, we actually deal with a lot of glass, right? So as you get into beams or configurations that need a really large aperture, we're dealing with a lot of glass at that point, which can be add to the weight or cost of the optics that you're dealing with, for example. But they both have trade-offs as well to the optical aspects of it too. Yeah, some a little bit more forgiving to polarization and spectral performance as well.
All right, thank you. And let's see, the next question here we have, what type of lens would you need to recover a circular spot from a stripe made by a cylindrical lens?
Well, so you would typically, you would need to use either a couple of cylindrical lenses in tandem to achieve this. An alternate approach is there are prisms that are available that allow you to circularize your beams as well. So those are referred to as anamorphic prisms or an anamorphic prism pair. So you can even get those from Thorlabs either in a loose configuration so that you can tune those angles specifically to the ellipticity that you observe, as well as in a fixed configuration if you're working with an ellipticity that's much more standard or defined to that existing orientation. And Matt, yeah, please feel free to chime in to elaborate on any of this as well if you have additional thoughts.
No, I think you're covering it all pretty well.
Thank you.
So it looks like we've got one last question here available. Yeah, we've still got a few minutes, so if anybody wants to put in any last-minute questions, we can address those still. So the question we have, yeah, you talk a lot about fabrication and trying to create very nice optical surfaces. Can you maybe explain a bit more why we care so much about a surface being so flat and pristine?
Yeah, that's a great question. So certainly a bit due to time, but also just a little bit of understanding of as we pass through these surfaces, if we don't have it perfectly flat, we'll see deformation to the wavefront, and this can really lead to either your image not appearing clearly or more drastically in cases where it's an interference-based system, we're not going to see the effects that we expect. So that's certainly a big aspect of why we need to have a very flat surface. And then beyond that, we also need to make sure that our roughness is very low on the surfaces. This minimizes the scatter that we'd see at the surface, either occurring uniformly across that surface or introduced by imperfections like scratches and digs. In those situations, yeah, looking to minimize that so that we have a nearly pure specular beam that's either reflected or transmitted from those surfaces.
Excellent. So that's all the questions we have here.
And then I guess just, yeah, lastly to that last question, if there's nothing else, is that we also find that it's very important that the surfaces are very clean. So though not touched on really here, it is very important that we make sure that those optics are as clean as possible. And actually where this image comes from is that we take great care to make sure to inspect our parts to these high qualities of low scratch dig and high cleanliness levels.
All right, thank you so much, Bill. We've got, looks like, a couple of last questions here. What is the largest optic you have ever made?
Here at Thor Labs, I think around 8 inches is roughly the largest size that we make, at least routinely. So as I mentioned, it is a common configuration for us to coat at those 8-inch sized wafers. One of the benefits we have there is that we can keep those substrates on hand, aside from the parts that we put to stock for catalog, so that we can quickly adapt to allow for customs and specials from that 8-inch part. Beyond that, I'd say for some of the stuff, the powered optics, so the lenses and such, I think we top out closer to around probably around 5 or 6 inches. And yeah, and Matt, once again, I know you, as handling a lot of our specials, might see some of the unique ones and might have some other thoughts there or neat examples to touch on.
Trying to think, yeah, any really large optics requests we've gotten. Yeah, I think the largest ones we see typically are around the 6 to 8 inch range. But yeah, I mean, I think once you sort of, as you mentioned, once you get to a given size, that weight becomes a consideration, and you sort of need to start thinking of potentially alternative ways to get something done. All right, so it looks like we've hit our time limit. We had a couple more questions come in at the end, so we'll reach out and address those offline. We really appreciate everybody stopping in and listening to our webinar. Thank you for your time.